Hello, and welcome to Physics 2212, Lab 3 Bar Magnets by Blake Schwabe. Purpose and the final results of this lab. So the purpose is to measure the magnetic field from a bar magnet at a distance with visual representation and to find the magnetic movement of a bar magnet. And the results of this would be N would be equal to negative 2.7729, and then mu would be 3.189768904 AM squared. And then fundamental concepts and equations that would be used would be the Biot-Savart law, and then the distance-dependent formula of the bar magnet, as shown here, and then a formula that is derived from that one. Experiment, very simply, you use your phone. You make it so it's orthogonal to Earth's magnetic field. That way the um, magnetometer is probably put in place for this experiment. And you need to find the um, magnetometer chip on your phone using a bar magnet and a ruler. Basically, you place the bar magnet next to the edge of the ruler, and then you basically find where X is the max and Y is the min. Then you tape it up, flip it 90 degrees, and then do the same thing. If that is a bit confusing, there's a demonstration on the bottom to show you what to do. And then you need to measure the distance between the bar magnet at the end and then the magnetometer chip. Do this for both both on and off axis experiments. The system itself is the bar magnet, and the surroundings is everything else for this experiment. Data. This is the bar graph that I got for all my data. Made sure everything was double checked through. Everything is fine. N that I got from the beginning was negative 2.7729. That's the slope of this line, and then the y-intercept that we're going to be needing would be negative 14.265. And then D, by the way, over here, the average is 0.162. That will come in a little bit later. So calculations. R would be 1 meter. And as we discussed was negative 2.7729. Y-intercept is negative 14.265. To find K, what we need for this, you need to actually find the inverse of ln, which is e to the power of whatever that ln was. So the negative 14.265, which basically gives you 6.4 times 10 to the power of negative 7. And then to find you here, it's very simplified all the way down, would be 10 to the power of 7, k r to the power of n plus 3, all of that over 2. When that is fully simplified, you get the answer of 3.189768904 AM squared. Now, this is the coding portion of it. What we just showed you, mu, back here. I plugged that up top, and then I basically created a function for magnetic field. I made sure the scaling distance were appropriate. I edited the observation locations to make them work. I then did arrows to represent the magnetic field on axis. And then over here, I did it for the perpendicular to the axis for this. And then add the d perp, and then had the arrows to represent magnetic field at a 45-degree angle. And then also did magnitude just to test. Now, with all that being said, the magnitude of B is 4.19, and it is about 50% off from the actual total, which there are many reasons for that. That being human error, measurements, not knowing exactly where the magnetometer is on your phone, and then some rounding. And then the assumption I made through this was the bar magnet acts as a magnetic dipole, which could be it, but in some situations that could not be it, and also there could have been other objects around it that could have affected it. So observations that I found was that the magnetometer, when far away from the magnet, would measure a near zero magnetic field in the x direction, and as it moves closer, the x component of the magnetic field increases. Now, what if and why? What if you had oriented your experiment to compensate for magnetic north, and had instead laid out your meostake in some indeterminate angle, intermediate angle with respect to Earth's magnetic field. Basically, the field were affected, messing and skewing with the results. And what if you added two magnets together end to end? What would that do? The magnetic field of it would double, but everything else would stay the same, specifically the distance. Not distance, sorry, the direction. Hope you enjoyed.